Okay, now the question becomes, what is it actually streaming to YouTube right now, given that I'm the only person in the room? Oh, all right. That actually works okay. Cool. That's interesting. It's live streaming a very different thing to what I'm seeing. Interesting. Okay, I think for this, OBS might be the way forward, or something like that instead. But we can work on that. So this will work for now. So starting at 4:10, we will continue on with this. I don't want to watch the stream at the same time. So moving forwards then. Welcome. I am the mysterious voice in the ether, speaking to no one at the moment, I assume. And we are going to be looking at an A2 physics paper today. So we have about half an hour. So I believe there should be 7 questions in this. Oh, it might be considerably more than 7. There are 11 questions in this. Wow. Okay. So we're looking at 3 minutes question here. So let's get cracking. Right. What is a gravitational field? That's just something you have. We're looking here at insights, at core tips for the maths questions, core equations, that sort of thing. We are not looking for me explaining things that you just need to know. That's in the mark scheme. That's there. You can look that up yourselves. Okay, solar system, Newton's law of gravitation. Ow, okay, my voice, I apologize for that. So, state Newton's law of gravitation. It's 3 marks. Oh, I don't have the pen. I need the pen, there we go. It's 3 marks. So, we know for a start that they are not just looking for the equation here. If they were just looking for the equation, we would not be giving that many marks away. So we're looking for it in words. Newton's law of gravitation. It is proportional to both the masses, to the product of the 2 masses, inversely proportional to the square of the separation, and essentially that they are point masses. So yeah, the only thing to say about that here is essentially that point of, if it's asking you lots of marks, if it seems too good to be true, it probably is. And in this case, it means they're looking for words, not just writing down an equation. Determine the ratio of gravitational field strength due to the sun at the orbit of Earth, due to the sun at the orbit of Jupiter. Okay, so what are we looking at here? Yes, so this is purely looking at the radii. We have the radii up here, 1 over r squared. So this is going to be r squared Jupiter over r squared Earth, because Earth is 1 over r squared Earth, and so on and so forth. So we're looking here at proportional to r squared j over r squared e. There we go. That almost looks reasonable handwriting. Continuing on very rapidly. Wow, 3 minutes a question is going to be tough. I apologize. So, orbital period of the Earth, use ideas about circular motion. So this is a useful thing, and it's a very important and a very, I think, a reasonably interesting thing and a nice thing to cover. It fits together very nicely, is this intersection of circular motion with our mv squared over r, mr omega squared, those kinds of things, and equating the centripetal force from circular motion to the gravitational force when we are dealing with orbits under gravity. And that's the key point. In circular motion, a centripetal force is provided. The centripetal force isn't some force that acts, it is some force that has to be provided to cause circular motion to happen. And in this case, that centripetal force is our gravitational force. And so by equating those equations, by equating the equation for centripetal force to the equation for gravitational force, that's where we get these kinds of things from. And then you just rearrange to put the mass on one side and everything else on the other side. You are also going to need omega is 2 pi over t for this. So there's that too, but yeah. Again, I'm not going to be writing things down because I don't really have time and my writing software isn't very good at the moment. Continue on. Orbital period is a number, radius. So at this point, you're just putting numbers into an equation. Be careful with your calculator and all that, but that's kind of that, essentially. You have an equation from up here, use it, is essentially the end of that. All right, so moving on to question 2. State what is meant by an ideal gas. Just something that you need to know, but it's worth noting the main points. Non-interacting small particles, elastic collisions. 2 cylinders, A and B, are connected by a tube of negligible volume. So essentially what that means is that you are to assume that they're connected, but that you can ignore that connection aside from the fact that they're in equilibrium with each other, or that they will be when this tap is open, presumably. Okay, so we have some volumes, we have some pressures, and we have one of them, we have a temperature. Initially, we have a tap closed, so they're separated. Cylinder A, constant volume, contains gas, and temperature, show its moles. So this is PV equals nRT. Let's write that down because that's the important bit here. PV equals nRT. Close enough. That's all we've got here. We have a pressure, we have a volume, we have a temperature. R is just a constant, this one here. It's about 8.3. So work out N from that. That one's nice and simple. The second one is going to be a little more tricky. So cylinder B has a constant volume of X and contains a certain number of moles of gas. When tap T is opened, the pressure of the gas in both cylinders is this. So now what we are dealing with this time is just once again PV equals nRT. We have a new volume. We have, so let me write it down again so I can highlight them. PV equals nRT. We have a new volume, which is just the volumes added together. We are given a new pressure. We are looking for a new temperature, and we know the number of moles because we've worked out the number of moles in one, and we've been given the number of moles in the other. And number of moles is not going to change unless you physically add more stuff, because number of moles is just a count of the number of particles that we've got. Okay, so again, putting numbers into an equation, but a little more thought going into that one, hence more marks. So, by reference to the work done and change in internal energy, suggest why the temperature of the gas in cylinder A has changed. So, this one is a little more involved. So, let's have a look at what they are after, first of all. So, they're looking for... Okay, so this is a point that I always have to make, stating the obvious. So one of this is not really a scientific insight, and this is something you can see for yourself, but on the mark scheme, they genuinely have a mark for the gas has moved from cylinder B to cylinder A. That is, yeah, they want you to state that. So yeah, state the obvious is a useful point to make. The reason that we know that the gas has moved is because the pressure in cylinder A started out at 3.4 and went up to 3.9. If the pressure has gone up, some gas has to have moved in to pressurize it. That's how we know that the gas has moved across. If the gas has moved across, then we're compressing some of the gas that was already in there, essentially. And so we've done work on it. And if we're doing work on it, but it says up here, no thermal energy, I've crossed it out instead of underlining it, but no thermal energy enters or leaves the gas. If none enters or leaves, then all of the energy that we're putting in, all of the work that we are doing, is going into internal energy. If our energy goes up, our temperature goes up. That is a trickier question. It requires quite a lot of thinking about and understanding the principles rather than just sort of plugging things into equations. A lot of the time, it seems that the mathsy ones are the hardest. I would argue that this is probably going to be one of the hardest questions on the paper. It requires a lot of understanding. The mark scheme is useful as a memorandum, but it's not something that you're going to understand the question from. So we know that the gas has passed because the pressure has gone up. We know that it's gone into cylinder A, and essentially that means that we've compressed cylinder A. We've done work on the gas that was already there. That is an increase in energy, and if we increase the energy, the temperature goes up. All right, moving swiftly on. A ball is held between two fixed points by two stretched springs. So essentially, we have a regular mass on a spring here. Those two springs will act as one spring of K1 plus K2, generally speaking. That's how this sort of works. Okay, use the figure, determine the amplitude. That's your height from here to here. The frequency, so we can work out the periodic time, and then we can say F equals 1 over T. T is actually the hardest letter to draw when you have some lag on your things. I've rapidly been discovering this. And show that the maximum acceleration. So maximum acceleration, this comes from our simple harmonic equation, simple harmonic motion equations. They are sinusoidal, so we know that the maximum of any sinusoidal curve is 1. So our maximum acceleration, mod A max, is equal to omega squared times the amplitude. We know that omega equals 2 pi f, which we just found, and we found the amplitude, so we can find the maximum acceleration. Okay, I've put the modulus signs in here because obviously acceleration can go in both directions. It'll be, acceleration will be at a maximum by here and by here. But it will be in opposite directions, so it will have opposite signs. But it's the same, and it's the same size of acceleration. Use your answers in A to plot on the axes the variation with displacement of the acceleration. So that is a slightly nastier one in a way. In fact, that is a very nasty one. But what we end up with is that, in fact, we know that our maximum acceleration is omega squared A, and our maximum displacement, by definition, is just A. A is the maximum displacement. That's what amplitude is. So actually what we know is that our acceleration is minus omega squared times our velocity. We can see that from the actual simple harmonic motion equations, which will be in your data booklet. And so what you will end up with is actually a straight line with a negative gradient that'll look, something like this. And its negative gradient should be gradient equals omega squared minus omega squared, because it's negative, it's slanting down. So that's what you're looking for there. It comes from, essentially, you have, let me just write them out here so that we know what I'm talking about, and then you can go back if you need to. X equals a cos omega t, and a equals minus omega squared, a cos omega t, and plus phi or whatever in the causes, because you can vary the phase, but that's the essential point. And so it's this minus omega squared here, and then this is just x. All right, calculate the displacement of the ball at which its kinetic energy is 1/2 the maximum kinetic energy. So here we are looking for V. So kinetic energy is proportional to V squared. So if we want half the kinetic energy, we're going to need 1/√2 times the maximum velocity. Our velocity is, and this is in your data books, omega a sine omega t. So we need our sine, well, more to the point, we're looking for our I see, you have some slightly curious. Oh, I see. All right. So I was going to say, for 3 marks, this is seeming like a rather involved piece of work. Apparently, you have an equation given to you in your data booklets using x0 squared minus x squared, which gives you the kinetic energy at a given displacement in simple harmonic motion. So you have an equation, you put numbers into it. That's a relatively simple question, in fact. I apologize. Yes, you have an equation, you put the numbers into it. The equation is apparently 1/2 m omega squared x0 squared minus x squared is your kinetic energy at a position x, where x0 is presumably, I'm unsure, presumably that's the amplitude, presumably. Anyhow, moving on, because we're only on question 4 and we are well into the half an hour. Okay, so define electric potential, that's just a definition. A charged particle accelerated from rest, show that the final speed is given by this expression. This is just equating kinetic energy and electric potential energy. So we know that VQ is our electric potential energy, and that has been converted into kinetic energy, 1/2 mv squared. So that's where our VQ is going to come from, and you can see that essentially this is just then a rearranged kinetic energy equation. So yeah, equate the kinetic energy it has at the end with the electric potential energy that it had at the start, and then lost as it was accelerated through a potential difference. So essentially it's moved from an electric potential of V up here, and it's moved down to an electric potential of 0. In fact, we don't know those exact values. Those exact values don't matter. What matters is that the difference here That's why it's called potential difference, is V. And therefore, that's how much energy that it has gained as it's gone through that. Particle specific charge, it's an interesting one. So specific charge, you can, this one is an interesting one. It's about determining what you're doing from the units. So specific charge, coulombs per kilogram, that is charge per unit mass, is moving in a vacuum towards a metal sphere of fixed potential. Our initial speed and when it is a long distance away. So first thing to note, they are both positive. So we're going to be repelling each other. Use the expression in B, which is our velocity after moving through a potential difference, to determine whether the particle will reach the surface of the sphere. So what we're going to do is we're going to say, okay, I need to say long distance. Oh, I see. So what we're going to say is we have a certain potential where we are, and were we to move to the sphere surface, we would have a different potential. We're going to work out that difference, and then we're going to determine the velocity. This is, okay, let's see what the mark scheme says here. So, right, yeah. So there are a variety of ways that they are interested in you trying to approach this. So we're going to take a step to look at this. V equals the square root of 2VQ over M. Now this is slightly unfortunate because we've got two V's and in my handwriting, so I'm going to put a dash on our velocity V and not on our potential V. So there are a variety of ways that we can consider this. The first point to make is we are at a long distance from the sphere. At a long distance, very far away, that is where we take electric potential to be 0. So we are moving from 0 to 470. Therefore, our big V in this is 470 volts. Or it would be if we were going to travel all the way. So probably the best way of doing this is to say, given that we have a certain velocity, which we know, we have a Q over M, which we know. So Q over M, charge divided by mass, which is exactly what this specific charge is telling us. So that's what we need here. So given that we know these two values, we can say that the potential that it is able to reach is equal to M over Q V squared over 2 by rearranging that. What we will discover is that that is in fact less than 470. So it's not actually able to get to 470 volts with the velocity it's got. It would need a bigger velocity, and therefore it won't reach the sphere. This is quite an involved question, and it's quite a tricky one because it is very deliberately dealing in an equation that you have never come across before and a situation that you are unused to. Again, this is a hard question, but if you are able to work through it logically, it sets you up in a very good position. All right, so moving on again. Define a Tesla, that's just a definition, unit of magnetic field strength. We have a long solenoid with an area of cross-section 28 centimeters squared. blah, blah, blah. All right, magnetic flux density at the center of the solenoid. You've just been given the equation written up here, B equals mu naught Ni. So we have a current, we have, okay, and N is a constant equal to, N is the number of turns per meter. That's what N is. So you've been given all the information, you can find B. That's just putting numbers into an equation. The flux linkage in the coil. So flux linkage is essentially, so B is the magnetic flux density. That is the flux linkage per unit area. So flux linkage is just BA. So all we need is the area of the coil, which presumably, hopefully, we have been given. Yes, 28 centimeters squared. So again, just putting numbers into an equation. Faraday's law, again, just something you need to know, unfortunately. Currents moving through a magnetic field and all that. The current in the solenoid is reversed in direction in a time of 0.8 seconds. Calculate the average EMF induced in coil C. So, Faraday's law in numerical form is the induced EMF is proportional to minus the rate of change of magnetic flux. So it's minus d by dt phi. That's maybe a little too mathsy if you don't do maths, but presumably you do. Essentially, what we are saying here is if we want an average, we are doing delta phi over delta t. When we do that, we will be doing double the magnetic flux linkage that we found up here because we've reversed it. So we've gone down to 0 and then back down to minus, and we've been given the time difference. So again, putting numbers in. That was a relatively complex topic in terms of inductors, but it was actually a very simple question because it was all just putting numbers into formulae. Okay, simple transformer. So few coils, many coils. It's going to increase the voltage. So these are just points that you need to know. Why is the iron core laminated? Reduces eddy currents. What is meant by an ideal transformer? No loss of energy. Just standard points. Ideal transformer has 300 turns and 8,100 turns. RMS input voltage is 9.0. Calculate the peak voltage across the load resistor. So here we are saying, all right, we have an RMS voltage. We can use our ratio of turns to calculate the new RMS voltage, and then we can multiply by √2 to get the maximum voltage. So 8,100 over 300 is going to be 27. So 9 times 27 and then times √2 will give you some number of volts. And that's it. Okay, that was a very short question. Fair enough. Yes, so this one is just using the whole V1 over V2 equals N1 over N2 for a transformer, and then needing to know that the root mean squared is the maximum divided by √2. Those are the key points. Shall I write that? I'll write that one down as well. RMS equals max over √2. Cool. For a sinusoid, that is. Some data for the work function. So now we are dealing we're turning over to quantum now. We're turning over to I've genuinely completely lost the words for it. What is it called? The photovoltaic effect. There we go. Wow. Unfortunate. I've been talking very rapidly for a very long time at this point. Hopefully it won't continue too much longer. Some data for the work function, energy phi. And the threshold frequency of some metal surfaces are given in figure 7.1. State what is meant by the threshold frequency. So again, this is just something you need to know. It's the minimum frequency of incoming light, of incoming photons, that will eject electrons. Calculate the threshold frequency for platinum. So giving the work function and the threshold frequency is a little curious because they are essentially the same thing. We are dealing in, by here, we are dealing in E equals HF, and in this case, E is our work function energy that we need to overcome. So our threshold frequency is going to be phi over Planck's constant, and that will apparently give you 1.4 times 10 to the 15, so essentially 14 on this scale by here. Okay, moving on. Electromagnetic radiation, having a continuous spectrum of wavelengths, is incident, in turn, on each of the metals. So determine which metals, if any, will give rise. So in this case, we are now saying, okay, we need F equals C over lambda for electromagnetic radiation, F equals C over lambda, and we need the maximum and the minimum frequencies, and we will determine essentially whether that maximum frequency is higher than the threshold frequencies. If it's above the threshold, they will emit. If not, they won't. Seems fairly reasonable. When light of a particular intensity and frequency is incident on a metal surface, electrons are emitted. Why? Essentially is what they're asking. So same intensity, higher frequency. So this is an important point. So light comes as photons. Intensity is how many photons are coming in per second. Frequency is how much energy does each of those photons have. That's a good way of thinking about it, right? So you've got photons coming in and each of them is holding a chunk of energy. Intensity is how many photons are coming. Frequency is how much energy are they holding. So if we have the same intensity, we've got the same number of photons, then our rate of emission is essentially going to look like this, right? Because either those photons are going to have the energy needed to emit, in which case they're going to be up here, and we have the same number and we have the same intensity, so that the rate that they're coming out at is never going to change, or we get to a low enough frequency that none of them have that energy, at which point we're not emitting at all. So it's this kind of block step function. If we're changing the frequency, then we're going to go from emitting to not emitting, but it's not going to change the rate because the rate is dependent on the intensity. Okay. Right, nuclear fusion reaction. So nuclear fusion reaction, we are combining two nuclei into one and usually, hopefully, releasing energy, unless you get past iron. Did they want that? Yeah, two light nuclei combine to form a more massive nucleus. That's what they were after. Okay, so this is everyone's favorite equation. People love using this because finally, after all these years, we've reached the famous equation. So here we are dealing with E equals mc squared. So what we need to do is we need to go from beginning to end. We need to calculate the mass difference, and then we need to convert that mass difference using our equation into an amount of energy. The temperature in the core of the sun is approximately hot, very, very hot. Why is such a high temperature necessary? So the reason it's necessary, the reason you need very high temperatures for fusion reactions, is because our nuclei are positively charged and we need to mash them together. And when you're trying to mash together two very, very positively charged things, they repel each other very strongly. And so if they're coming in and trying to collide with each other, and they aren't going fast enough, they're just going to fly away from each other again. They need to get in very, very close before they are going to fuse. So you need to have high enough kinetic energy, high enough temperature to overcome the electrostatic repulsion of the two positive nuclei. I'm not going to go into the quantum tunneling facts. That's rather too much for this, I suspect. All right. 9, suggest electrical sensing devices, one in each case that can monitor changes. So light, what do they want? I was going to say they definitely don't want a photometer. So yeah, light-dependent resistor, strain gauge, and a piezoelectric crystal is what they are after here. These are just things you need to know, apparently. So we'll just continue on. So this is all about sensors, essentially, and sensors in terms of electric sensors, more specifically. So what we are actually dealing with here, even though they didn't say it, oh yes, they did, okay, electrical sensing devices, but they meant it in a more specific way. What they mean here is resistance sensing devices. So what we're talking about is saying we have a resistor which is changing resistance in response to some outside stimulus. And we are going to use that to measure that. So in this case, does V out increase or decrease as the temperature of the thermistor increases? So our thermistor resistance is going to increase as our temperature goes up, because that is how resistance works. V out is proportional to R over R total, and therefore as R total goes up, V out is going to go down. So V out is going to decrease as the temperature increases, or it should. Oh no, okay. Apparently our resistor of our thermistor is going to decrease as temperature increases. That is interesting, but okay. Apparently that's what they're doing, and that's what we're going to go with. So in that case, the logic is reversed. R total is going to go down, and so the proportion going into V out is going to go up. And the fact that your board determines that thermistors go down as temperature goes up is something that you just need to know. Does it vary linearly? I would doubt it. So no, it is non-linear. There we go. Again, just something you need to know. Thermistors are definitely non-linear. All right, 10. Distinguish between sharpness and contrast in X-ray imaging. Interesting. So sharpness is how sharp the edges are, and contrast is the difference between a light bit and a dark bit. The degree of blackening between structures is how they have defined it in the mark scheme. 2 causes of loss of sharpness. All right, so essentially these ones, so they've got scattering and large pixel size. I mean, depending on what you're using, you don't necessarily have pixels in an X-ray image, but that's beside the point. These are just things that you need to know. There's no deep insight into that, I'm afraid. Data for the linear attenuation coefficient. So here we are just dealing in an exponential equation. We have I equals I naught e to the minus mu x, where x is presumably distance. Yeah, so, and then we're putting one over the other. So it's going to be e to the minus mu of bone over e to the minus mu of muscle for the given distances. That seems fairly reasonable. You've been given numbers. I naught doesn't in fact matter because it's going to divide out. There's not much more to say about that. This exam, these papers are very keen on these ratio questions. So it's important to get used to spotting what is going to divide out. Yeah, not much more to say there. Use your answer to suggest whether an X-ray image of the bone and muscle would show good or poor contrast. So in this case, we are looking for, is it a large ratio or a small ratio? If the ratio is near 1, then it's going to be a very poor contrast because they're pretty much the same. If it's very large, it's going to be a very good contrast because they're going to be very different. Or indeed, if it's much less than 1. Big or small doesn't make a lot of difference. But near 1 is bad contrast, very small or very big is good contrast, because it shows a large difference. Okay. Last one. Amplitude modulated wave for the transmission of music. So what is meant by an amplitude modulated wave? So they have defined it as the amplitude of the carrier wave varies with the displacement of the information signal. It's a very interesting way of phrasing it. But again, just something you need to know. Why do we modulate it? Again, just things that we need to know. It basically makes the technology itself easier. It's for interference reasons rather than because it actually helps with quality or anything like that. Variation of frequency of the amplitude is shown here. So for this transmission, determine the wavelength of the carrier wave, the bandwidth, and the maximum frequency. Oh, there's 12 questions, blimey. This paper is absurdly long. So wavelength of the carrier wave, that's just frequency. So we have our middle frequency by here. Wavelength, lambda equals c over f. That's pretty reasonable. The bandwidth in kilohertz is going to be presumably 18 kilohertz, yes, because that's just the width. And the maximum frequency is of the transmitted audio signal. It's apparently, oh, I see, yes. And so the maximum frequency is the lowest frequency of that we are reaching overall, because otherwise we wouldn't sometimes reach it. Yeah, these are just, again, this is essentially, it's reading from a graph, so it's skills, but these are just things that you need to know about very specifically amplitude modulation graphs. It's not a transferable skill from anything else. This is just stuff you need to know how to do off of this. I'm not sure that there's much to say there. All right, so yeah, we've kind of run over a little bit, but let's just briefly do question 12 and then we will wrap up. So optic fiber, we have power input. Calculate the minimum input signal power to the receiver. So power input to the optic fiber is 9.8 milliwatts. Okay, so our signal to noise ratio must not fall below 28 decibels, and calculate the minimum input signal power. So essentially, we are looking for what signal power is going to give a ratio of 28 decibels or after we have attenuated it over the wire, over the length of the optical cable. That is just putting numbers into an equation at that point. So yeah. Yes, that's about it really. Okay. I think they've slightly misworded this question, but okay. That should be the end of the paper, shouldn't it? Yes, that is the end of the paper. Okay. There is, so attenuation is in decibels per kilometer. So that's just dividing this attenuation that you found here. And that you are finding from an equation. However, I must admit, I don't know the equation. I haven't dealt in attenuations like this before. This is a slightly odd setup they're using here to avoid dealing in. They're avoiding a slightly more complicated topic that you would do otherwise. And I'm afraid I haven't dealt in it before, so I'm going to have to leave that one for the time being. My apologies for that. All right, so slightly unfortunate ending to that. However, we will leave that there. This was a slightly all right, well, leave that for now. I hope that this has been all right for you guys, for anyone watching. This was a first attempt. Hopefully these will get better with time. It was slightly rushed. I think these A2 papers take longer to go through than the AS ones. So, yeah, hopefully that was good, and we will stop there. All right.